Okay. Now, we will begin our discussion on longitudinal modes, but before we do so, we have a question. What is the question?
Actually, no, we have seen what is the power per pulse, but how to find out the peak power?
So, the question is how to find out peak power. To find out peak power, it is important to realize that what we see here, it is the power or energy per pulse, it is basically area under the curve. So, from there, suppose the pulse is triangular, it is easier to understand triangles, that is why I am saying triangular, we will come to Gaussian. Suppose it is a triangular pulse, then your area is half into base into altitude. So, from there, if you know that we had taken 200 femtosecond to be the width, that is the base, you can find out what altitude is. And here the point to remember is that the base is really very small. So, half into base into altitude, base is small, so altitude will automatically become very large. And now, for a more realistic situation where we have a Gaussian kind of distribution, there what we will have is we are not going to have half into base into altitude, but even Gaussian has a line shape, right. It is I0 intensity at the maximal position multiplied by a Gaussian distribution, e to the power minus x square by 2 or something like that. So, from there we will still be able to find out I0. That is how you find peak power, and for small pulses and same kind of energy, peak power is really, really high.
So, for in-field where they have kind of described the damage threshold, it is from the perspective of peak power or average power?
Damage threshold is usually peak power, not average power, because damage is a result of one-to-one interaction of light and molecule, right. So, sometimes what happens is that you know what kind of laser you are using. So, in that case your peak power is proportional to the average power, and proportionality constant is known, the system is known, then average power may be mentioned. But what you really have to worry about is if you have short pulses, peak power is the killer if you are worried about damage of your system. Sometimes damage is good because you might want to do lithography, or you might want to do laser cutting or something like that. In a favorite example of mine, nothing to do with spectroscopy, to be honest, I do not exactly remember the year, most likely sometime in 2003 or 4 or something like that, there was this interesting paper in which somebody had manufactured a bull, the animal that is rampant in our campus, bull, a he cow, a bull. Now, of course, being in IIT Bombay, one might wonder what is the need of manufacturing bull. God has manufactured plenty and they have provided plenty of problem for us all the time. But this bull was special, this bull was a nano bull, so it would not provide too much of a trouble to you. And the way they worked, they just wanted to demonstrate, there is no reason for making a bull otherwise, because you cannot even see it unless you put it under a microscope. But the way this bull was prepared was that a pulsed laser was focused onto this monomer solution, and the idea is that the light that you put in it is going to cause polymerization. So, wherever the focal point is, that is where polymer will be formed, and then you move the stage carefully and the polymer bull is formed. Okay, it is nice, very, very good, nice, good looking bull actually, you can read that paper. But then the point that I am trying to make here is that it is focused, right, and you are talking about damage threshold. Here this is not damage, this is the threshold that is required for the reaction to happen. And then if you want a very good resolution, so here the trick that was played was 800 nanometer light was focused, but actually 400 nanometer light was required for polymerization to take place. So, polymerization took place as a result of 2 photon excitation. Now, 2 photon cross section is actually square of intensity, right. So, it is narrower than the actual pulse. That is why better space resolution was obtained by focusing light not of 400 nanometer, but of 800 nanometer. I do not, perhaps we digressed a little bit to answer that question, but intrinsically they are related. Something that can destroy can also build if it is used properly. Right. Now, let us come back to a point of discussion. We want to talk about longitudinal modes. Now, you might think what is going on here? What is where did this come from? We are talking about lasers, we are talking about pulse lasers, we are saying that you pack many photons. In all this discussion, what is the meaning of longitudinal mode and what is the relevance? I cannot say what the relevance is right now. You have to wait maybe 15 minutes or 20 minutes to arrive there. Okay? So, let us first understand what these modes are. As we mentioned in the previous module, there is something called transverse modes. Transverse mode means spatially what does the laser beam look like. If you take the laser beam, laser spot on a piece of paper, do you get a circle? Do you get a dumbbell? Do you get something that looks like a d orbital? And there, depending on the number of nodes along x and y direction, you call them TEM 00, TEM 01, TEM 11, so on and so forth modes. But right now, well, they are important, we will come to them later. Right now, we want to talk about longitudinal modes. Longitudinal means modes along the direction of propagation of laser light. Okay. So, now it is important to understand that for a given cavity, not all wavelengths are going to be sustained, because in order to get a beam where light is going back and forth, you must have constructive interference, right. Standing wave has to be generated, and condition of standing wave is that the cavity length L, this one, must contain an integral number of half wavelengths, L equal to n lambda by 2. This is very well known, I think all of us understand that. Okay. So, the point we are trying to make is that you make a laser, L is defined, you decide already that a particular set of wavelengths can be sustained. Okay. In principle, this number of wavelengths is infinite, because n can go from, what is the smallest value of n? Cannot be 0, 1. N can go from 1 to infinity, but then also you have some active medium, right, which has a spectral bandwidth. It is not going to give you 1 to infinity. Okay. So, how many modes are there in the bandwidth that we are using? That is something that we will learn first. Why we are learning all this? We will see by the end of this module, hopefully. So, before going further, I want you to calculate this n, and the reason why I want you to do this is it is very easy to now think that okay, L equal to n lambda by 2, take a tisophyre laser. Since I have used 900 nanometer here, I will take that number. 900 nanometer is a wavelength that is sustained in tisophyre laser. Perhaps that is n equal to 1. So, n equal to 2, for n equal to 2, what will be lambda? What will lambda be? It will be half of that. N equal to 3, it will become 1/3 and so on and so forth. But that is actually not the case we have, as we will see. So, we want to dispel that notion, that is why we have to once again get a sense of numbers in this business. So, my question is, for lambda equal to 900 nanometer and L equal to 3 meter, this is a rough number that I am using here, what is the value of n? Can you calculate? Yes? 6.6 into 10 to the power 6, I have written 6.67 because it is 6.6666. 6.7 10 to the power 6, that is the first thing to understand. We are not dealing with n equal to 1, we are not dealing with n equal to 2, we are not dealing with n equal to 3, we are dealing with n equal to a very, very, very large number. Okay? If we are dealing with n equal to 1, 2, 3, we would actually have single mode lasers, because n equal to 1 and n equal to 2 would differ largely in the wavelength, is not it? So, it will be very easy to cut out one and use another one. Use an optical coupler, use an output coupler that is a dichroic mirror. Everything other than n equal to 1 or n equal to 2 or n equal to 3 would be cut off. Here, however, it is important to understand, first of all, the n value that we use is actually very large. Okay. So, if n is equal to this 6.7 into 10 to the power 6, what is the value of n plus 1? 7.7 into 10 to the power 6, 6.7 into 10 to the power 7. You do not even want to answer that question, because it is best to say 6.7 10 to the power 6 in bracket plus 1. Otherwise, you actually have to write down all those zeros, 6, 7, 0, 0, 0, 0, and then finally 1 0 becomes 1. Okay? Point we are trying to make here is n and n plus 1. Okay? Delta n by n is a very small number. Delta n is of course 1 when I am talking about n and n plus 1, but delta n by n is a very small number. Okay? How does that matter? This is how that matters. N into lambda n equal to 2L, n plus 1 into lambda n plus 1 is also equal to 2L. Okay? And what we just said is that this n and n plus 1 are practically the same. If n is equal to 1, then n plus 1 would be twice n. But n equal to 6.7 into 10 to the power 6, that plus 1 is practically equal to 6.7 into 10 to the power 6. If your salary is 1 crore rupees, you do not really mind whether 10 rupees are added or subtracted, right? It's something like that. So, now what will be delta lambda? Let us do a rough calculation first. Lambda into lambda n minus lambda n plus 1, what will it be? It will be a very small number, right? It is going to be basically 2L divided by n. Now, which one will be longer? Lambda n plus 1 is higher energy, right? No. Yes. So, the difference is going to be not much, that is what we understand. So, and that tells us why it is so difficult to make multimode lasers. See, you have maybe 900 nanometer and 900 and 900.5 nanometer, right? These are two successive modes. How will you separate them? Okay, that is why multimode lasers, usually lasers we have are not multimode lasers, and multimode lasers are available, but they are costly. For our purpose, this is a blessing in disguise, because if you want to do ultrafast spectroscopy, you do not want a multimode laser, as we will see. Okay. For now, it is important to understand that the difference between the wavelengths of successive modes is really very small, right. That is best understood if we take this problem of separation in colors of longitudinal modes, let me call them colors, in terms of not lambda, but nu, because energy is proportional to lambda, right. Energy is proportional to nu, reciprocal with lambda. So, nobody works with delta lambda, generally delta nu is better. Can you tell me what is delta nu? When delta nu is nu of n plus 1th mode minus nu of nth mode. Can you work it out? Delta lambda equal to nu n plus 1 minus nu n. What will it be? You have to convert this expression of lambda to nu, of course. Lambda nu equal to C. So, lambda is C by nu. Very small is already established. I am not asking for that, I am asking for an expression. I have two answers, one is C by 2L, another one is more complicated. What is the right answer? C by 2L, right? C by 2L. Delta nu, which is the difference in frequencies of two successive modes, it turns out to be C by 2L. Very interesting. Why is it interesting? It is interesting because it is a constant. You are working with some laser, right? L is defined and C is defined anyway, unless you change the medium or something. So, C by 2L is a constant. That is the first amusing information that comes out. Okay? Delta nu is constant, and the only thing that determines what delta, how big or small delta nu will be is L, all right. So, if you want delta nu to be double the value that it is right now, what do you do to the cavity? Do you increase, do you decrease? Yeah? Do you make it double, do you make it half? I want delta nu to become double, yeah? Then L has to become half, and I want delta nu to become half. That means I want the I want more energetically more closer modes. Then do I need a shorter cavity length or do I need a larger cavity length? I need a longer cavity length. This is an important issue, and this is an important issue for both, depending on your requirement. Do you want more modes, do you want less modes? That is the first control. As you will see, we want more modes if we want an ultra fast pulse. So, for that you have to increase the cavity length. Okay? Where was the first femtosecond pulse produced in India? Bangalore is an answer. Bangalore, no. In this case, no. I gave you a hint. I am asking the question. And of course, it is not our lab. It was produced in IIT Bombay. It was produced in Department of Physics, Professor B.P. Singh's lab. He had a CW Tisaphier laser. So, if you go to his lab, even now it is there, you can see it. He made a very strange arrangement. He opened up the laser and then he added a vertical invar rod on which he mounted optics. That is how he increased the cavity length. So, you can actually buy Tisaphier lasers that will never give you pulse, always CW, and you will find that they are very small. Our Tisaphier laser is first of all big, secondly it has folded cavity. We are going to open it up and we are going to demonstrate. That is because you need a certain cavity length in order to get pulse, and then if you want to be a straight cavity, simple 2 mirror cavity, then you need a huge space. Your table is going to be from there to here. So, it is better to fold it. Okay. By folding is done by using mirrors. Okay. So, C by 2L is a constant for a constant cavity, and if you want more modes means smaller separation between modes, you want the cavity to be bigger. That is the first point. What is the second point? C by 2L, that is a very special number. What is C by 2L? Okay, I will make it easier. What is 2L by C? 2L by C is the round trip time, right? 2L by C is the round trip time. You start at this point, let us say, hit this mirror, go back, hit this mirror, come back. That is called a round trip. So, the total distance travelled by the photon is 2L, right? And it is a photon, so it travels at the speed of light. So, 2L by C is the time for a photon to do a round trip, okay? Not you or me to do a round trip, photon. So, C by 2L essentially is the reciprocal of round trip time, okay? Incidental, but interesting, important. Now, I have written in terms of delta nu. Nu is something that I am not very comfortable with. I understand wavelength and wave number better. If I want to write delta nu bar, what will it be? Yeah? I think that is an easy question. Delta nu bar? That should not take so much time. Yeah, divided by C, what is it? 1 by 2L. You are hesitant to give the answer because it is so simple, but sometimes you get simple answers to difficult questions. What is the problem with that? So, delta nu bar is 1 by 2L. Okay. The only thing that matters is the cavity length. Now, let us once again do a quick bit of math. We are working with 900 nanometer, let us stick to 900 nanometer. Can you tell me what is nu bar for 900 nanometer? What is the wave number corresponding to 900 nanometer? 1 by 900 into 10 to the power 9, 10 to the power minus 9 of course. Okay. If I want to do mental arithmetic, it is easier to make it 1000, right. So, 1000 is 10 to the power 3, 10 to the power 3 into 10 to the power minus 9 is 10 to the power minus 6. What was that? Is that right? Yes, the reciprocal of that is 10 to the power 6. So, that is your nu bar for some nth one, nth longitudinal mode. What is delta nu bar? So, nu bar, what did we get? 10 to the power 6, right? 10 to the power 6, what is the unit? Meter inverse, right? See, once again I was going wrong by a factor of 10 to the power 2. This is my problem. So, 10 to the power 6 per meter, meter inverse. And what is a typical cavity length? Meter, 1 meter, 2 meter, 3 meter, does not matter. Okay. We had taken 3 meter earlier, is not it? So, let us say 3 meter. So, what is delta nu bar? 1 by 6 per meter, is that right? If L equal to 3, 1 by 12 is 10 to 1 by 12 is 1 by 6. What is 1 by 6? So, now you see this is what we are trying to say. Nu bar for that 900 nanometer light is 10 to the power 6 per meter, and nu bar for the next line is 10 to the power 6 plus, or if you take on the other side, minus 1 by 12, very close. Okay. Successive modes are actually very close in energy, because we are dealing with high n values, we are not dealing with n equal to 1, 2, 3. Are we okay? Clear? Can we go ahead? All right. Now, we want to know how many longitudinal modes are there. Why are we doing all this? Because we are going to see eventually that we want to take these modes and bunch them together to get the pulses. Okay. So, we want to know, before going there, how many longitudinal modes are there. To do that, let us have a look. All this is from that book whose author's name I cannot pronounce. I had shown the book in during the first module, I hope. Introduction to Laser Spectroscopy, Halina, and I cannot pronounce the second name. All right. Here, let us consider this. Okay, this is the laser cavity we have discussed many times. Here, let us say this is the spontaneous emission band, intensity versus lambda. Okay. Let us say spectral maximum is at lambda 0, and let us say delta lambda is half width at half maximum. See, what will happen is stimulated emission band is always narrower than spontaneous emission band. Okay. The energy density matters, isn't it? Energy density of this light is going to be very small. Energy density of this is maximum. So, this is sort of like the story of the bull that we were discussing a little earlier, nano bull. Okay. There also there was sharpening in space because you required a 2 photon cross section. Here we get a spectral sharpening because of variation of energy density. Okay. So, let us say, of course, this may not be correct for all systems. Let us consider that this is where onset of stimulated emission takes place. Okay. Half width at half maximum of the spontaneous emission band defines the half width of spectral base of the stimulated emission band. Okay? It is not necessary that it is half, it can be 1/3, it can be 1/4 something, but for now let us work with half. Let us say that this spectral width is delta lambda. So, what is the base of the spectrum? 2 into delta lambda, right. So, once again we are back to the question that we started with, but in a different domain. That was in time domain, this is in wavelength domain. Okay. So, now see, n multiplied by lambda n equal to 12, fine. N plus 1 multiplied by lambda n plus 1 equal to 12, that we know. Let us say your n max is the mode number. So, you are giving roll numbers to modes, mode number 10, mode number 11, mode number 12, it is just that we know it is not 10, 11, 12, it is 10 to the power 6 plus minus 1, 2, 3, 4. Okay. So, let us say n max is the mode number in this position. Where will n max be, here or here? It will be on the lower wavelength side, right. Lower wavelength is higher energy. Let us say n min is the mode number for this end of the spectrum. Okay. So, we can rewrite these equations then. N max multiplied by lambda 0 minus delta lambda should be equal to 12. N max is the mode number here. What is lambda? Lambda is this lambda 0 minus delta lambda. So, n max multiplied by lambda 0 minus delta lambda in bracket is equal to 12. Similarly, n min multiplied by lambda 0 plus delta lambda in bracket is equal to 12 once again. Okay. Have you understood? What is the total number of modes? N max minus n min. Well, you might want to do n max minus n min minus 1. Okay, but then n min minus 1, n min are not very different from each other. N max minus n min, what is that? N max will be equal to 12 divided by lambda 0 minus delta lambda. N min will be 12 divided by lambda 0 plus delta lambda. So, basically you are subtracting one from the other. You will get a denominator of lambda 0 square minus delta lambda square, is that right? And then you will have lambda 0 plus delta, in the numerator you will have lambda 0 plus delta lambda minus lambda 0 minus delta lambda. So, in the numerator lambda 0 will cancel, you will be left with, yes. Is this what you have got? Yeah. And what is the denominator? Lambda 0 square minus delta lambda square. But then what we have established so far is that delta lambda is really a small value. So, you might as well neglect its square. For a small value, square will be even smaller. So, what will the denominator be? Lambda 0 square, right. So, this is my answer, 4L delta lambda by lambda 0 square. Is this an absolute relation or does it change from case to case? See, this relationship is obtained with certain considerations. First consideration is the onset takes place, right, at lambda 0 minus delta lambda and lambda 0 plus delta lambda, where delta lambda is half width at half maximum. That may or may not be correct, it can vary. It depends on the shape of the spectrum and so on and so forth. Roughly you get something like this. You will definitely get L delta lambda in the numerator, you will definitely get lambda 0 square in the denominator. That 4, instead of 4 it can be 4.12 or 3.89, it can vary a little bit depending on what kind of spectrum you have and what kind of system you have. But roughly this constant multiplied by L delta lambda by lambda 0 square will hold. Okay. Now, we are in a position to look at this and think what n is going to be. We will actually work out given some typical values, but If L increases, N is going to increase. Okay? That may or may not have occurred to us if we did not see it. It would not have occurred to me for sure. If delta lambda increases, N will actually increase. I would not have guessed it, to be honest. And lambda 0 square in the numerator, denominator, that also would cause N to increase. Okay? If lambda 0 decreases, N will increase. Okay? Now, let us work it out for our tie sapphire laser. Maximum is at 800 nanometer, right? So, lambda 0 is 800 nanometer. L, okay, what is the value of L? Let us take 4 meter. Will it help? It will help to some extent, yes. So, let us say L equal to 4 meter. What is a good value of delta lambda? Where does lasing start for tie sapphire laser? Say 700 nanometer. Let us say 100 on each side. Okay, 200. No, 100, right? So, let us say delta lambda is 100 nanometer. Can we work out what the number of modes is under that spectrum? 4 multiplied by L is 4 meter multiplied by delta lambda is 100 into 10 to the power minus 9 meter divided by, divided by is too much. What is this divided by? What is the denominator? 800 nanometer square. So, 4 into 4 is good, that we will take care of, multiplied by 10 to the power 2 square is 10 to the power 4 multiplied by nanometer square, right. So, 10 to the power minus 18 will be there. So, these 4's all take care of each other. You are left with 10 to the power minus 7 in the numerator and in the denominator it is 10 to the power minus 14. Is that right? What is the number that is coming? How did you get 25? 4L delta lambda by lambda 0 square. Delta lambda is 100 nanometer. So, yeah, what is your answer, Vikas?
25 into 10 raised to 5.
Do we get that answer? How much? 2.5 into 10 to the power 6. Large number, right? So, we can expect that for something like titanium sapphire, the emission is very high, the stimulated emission is very highly multimodal. 10 to the power 6 modes are there. Now, let us see what happens in two cases. One in which these modes are have no phase relationship, one in which they have some phase relationship. This is what happens. Here, to keep things simple, we are not plotting intensity, we are plotting the time evolution of electric field. So, I am showing a large number of waves here, okay? Waves whose frequencies are different from each other just a little. So, this is a free running laser in which these different modes have no relationship, let us say. And here this is called a mode lock laser, and we will see why it is called a mode lock laser, where delta phi equal to constant, which means some phase relationship is maintained. The easier thing to work out here is at some points, let us say at this point, phase difference is 0. Now, what happens? You see this kind of a oscillation here, and here you see that at this point everything is in phase. Okay? So, if this is in phase, all the electric fields will add up, you will get constructive interference. The moment you move, x axis is time, remember. The moment you move out in any direction, the waves start getting out of step. This is something that we might have studied when we studied time domain spectroscopy, right. So, they start getting out of phase until they have complete destructive interference, and then after some time they will start getting back in phase. So, you are going to get something like these are called interferograms. Okay. So, you have packets of energy at regular intervals. The interval is shown here, we are going to derive this next day, but just see what the interval is. 3L by C minus L by C. What is that? 2L by C. Same 2L by C that we encountered earlier. And this is telling us a story. What is the story? The story is like this. Suppose you have a shutter in the cavity. Okay? You open it for a very short duration and close it again. What will happen in this short duration is that some waves will go through. Now, let us say you somehow manage to ensure that at the time of going through, all these waves are in phase. Okay? They come back. When they come back to that shutter, again you open it. So, what do? Then you sustain this mode locked operation rather than free running operation. Okay? So, you are basically bundling together waves that are in phase at that point of time of crossing the shutter, and then let them evolve by themselves, so that they will go to 0 very quickly and then come back. That is how you prepare pulses. Okay? This is only an introduction. In the next couple of modules, we are going to do the math, and then we are going to say how it is actually experimentally done. Okay? That will be our discussion of mode locking. If it is not ultra fast, then it is perhaps easier to do. If you want nanosecond pulses, it is done by something called Q switching. If it is femtosecond pulses, then things become difficult, and fortunately, as we will see, nature provides us a way out by which femtosecond pulses are produced by themselves. You only have to perturb the system a little bit, and the system mode locks itself. Okay? That is what we want to do after this. We may or may not discuss how to mode lock immediately right away after this, but rather after we have developed the concept of how to prepare, how to make pulses, we want to talk about how to amplify them. And then we come to the concept of chopped pulse amplification. Then we take it from there.